Alright, here in this video, I have a few additional rotational dynamics ratio type questions for you to follow here. The first one being this one. Here you have a solid cylinder and a ring that are released from the top of the same inclined plane, and it wants us to find the ratio of the velocity or the linear velocity of the cylinder relative to the linear velocity of the ring. Alright, so let's go ahead and crack this out. So here your answer choice is A, B, C, D, E. So I'm just going to go ahead and solve for V cylinder and V ring and really essentially just set it up over like this fraction or ratio here. So I'm just going to go ahead and start with this particular function for rotational dynamics for an object that rolls down the ramp. V square is equal to 2gh divided by 1 plus the coefficient of moment inertia. I want to keep my work here as V square. Even though the question asks for V over V, I want to solve for V squared just so I don't have to deal with the radical sign. So it's up to you. Like I said, I'm going to go ahead and keep this V square so I don't have to deal with the radical sign, okay? So I'm just going to essentially apply this particular function twice. Here, I'm just going to carry it down. I want to apply this particular function for the cylinder. So 2gh, both of these objects are released from the same height, so g and h will be a common term for this particular problem. The coefficient of a cylinder is going to be 1/2, and then I'm just going to go ahead and simplify my work here. Here you have a 1 plus a half, which is really 1.5, which is 3/2. But if you want to, you can break this 1 up into 2 over 2. This way you have a common denominator. So 2 plus 1 on the top here is going to be 3. And then the common denominator for the bottom term here is going to be a 2, so it'll be 3/2. All right. So if I can just clean it up, the top term hasn't changed, so it's just 2gh. 2 over 2 plus 1 over 2 is 3/2. And then as you can see here, you have a term in the numerator that's being divided by a fraction. So the rule, again, in math is to multiply by the reciprocal. So if you do that, you'll get 4/3 gh. All right, so once again, I have this is a V squared term. I'm going to do the same for the ring. Really the same process here. So I just bypass a lot of this algebra stuff. The coefficient for the ring is going to be a 1. 1 plus 1 is 2. And then 2 on top, 2 on bottom cancels out. And then essentially, you just have the V squared ring as just GH. All right. So, well, what do we do with these two terms? You just set them over each other. The ratio is V cylinder over V ring. So I'm just going to put V cylinder squared over V ring squared. So I'm just going to substitute in for what I just found. V squared for the cylinder is 4gh over 3, which is in the numerator there. And then V ring square is just GH. So therefore, I just go ahead and simplify this a little bit. This is a fraction on top divided by a whole. So essentially, when this algebra presents itself, you just combine the two denominators. So this is where you don't multiply the reciprocal, right? You only multiply the reciprocal if the denominator is a fraction. Here in this particular example, the numerator is a fraction. So if that's the case, just combine the two denominator. So it's going to look like this. So 4gh over 3 times gh. And as you can see here, the g and h on top and bottom cancels out. So essentially, it leaves you with just 4 over 3. But that's not your answer, right? Because these are V squared term. Well, how do you get these terms to just be V and not V squared? Well, you use square root both sides. So square root both sides will leave you just V cylinder on the top, a V ring on the bottom. And then the whole right side is radicalized. So it'll just be 4 over 3. So the answer is going to match. Let's see which answer choice D. Okay? So that's the first example. Let's do this one. Here in this problem, it says the solid cylinder starts rolling down, and then it has a certain V or VCM at the very, very bottom of the ramp. And it says if a block, on the other hand, starts to slide down from the identical plane, it wants to know what the velocity of the block is in terms of the VCM of the solid cylinder here. So I'm just going to go ahead and start with my fundamentals here for rotational dynamics. Once again, this is a function you just saw in the previous example. Here I'm just going to apply it. The reason I want to solve for 2gh here is because, well, 2 is a constant, g is a constant, and h is a constant for this particular problem because in this example, one of the conditions that they start from the same height, so h is kept the same. Okay, I'm going to solve for 2gh because all this to me is a constant. And then I want to do the same for the block sliding down incline. However, just to help you recall in case you haven't practiced this stuff, for the incline, block sliding down a smooth surface, the gravitational potential initially is going to equal to the Ke at the end because there's no friction loss due to friction because it's smooth. So here in my work, I just have P gravity initially is equal to Kef at the very bottom. Well, you can break these terms up. PE is just mgh, and then KEF. Again, the block is sliding, so it has no KE rod. It's sliding. It's not rolling. So therefore, KEF here is just KE linear, which is 1/2 mv of the block square. Here, mass is going to cancel out, as you can see. And then I'm just going to go ahead and move the 2 to the left side. There's a 2 on the bottom here, so I'm just going to multiply both sides by 2. I'm going to do that just so I have a 2GH in my first work for the solid cylinder. I also have a 2GH for the block. Well, now that you have two expressions for 2G and H, which are constants in both of these shapes, rolling or sliding and rolling down the ramp, I can just set these two equal to each other. So I'm just going to go ahead and take the function for the solid cylinder, which is V cylinder square times 1 plus C. And I'm going to set that equal to V block square, because that's a true statement. So again, learn to identify constants and then to set them equal. So here, I'm just going to go ahead and substitute in C for the solid cylinder, which is once again 1/2. And then we can just clean the parentheses up again, which is 3/2. So if you kept up with the first example in this video, hopefully you can do fractions, okay? 1 plus 1/2 is just 1.5, and 1.5 in fraction is just 3 divided by 2. Here, all we have to do really is just solve for V block. Well, V block here is squared. Well, how do we get just V block when you need to square root both sides? So if you square root V cylinder square, the square disappears, and then here the 3/2 will just go underneath the radical sign. So this answer is going to look like, let's see, V cylinder, which is just V in the problem, and then radical 3/2. So that'll be, let's see, that'll be choice D for this one. Even though the V is on the right, really, as you're multiplying, so you can put it on the left side. But what's important here is what's in, I think, underneath the radical, which is 3/2. All right, so I'm just gonna go ahead and highlight D as my answer. Let's move on to the next one. So here, in this particular one, you have a time ratio problem. You have a solid sphere and a solid cylinder. Okay, so here's a solid cylinder, a solid sphere. They're both the same mass and they have the same radius. All right, so it wants us to find the time ratio. We know that they have different acceleration if you've seen the other videos. So because they have different acceleration, they'll take different times to get down to the bottom of the ramp. Well, I'm just going to call the length of the ramp here L, and then using my kinematics equations from review, I know that the acceleration for these problems are constant, so I can kick in these kinematics function. So instead of delta x here, I'm just going to call the length of the ramp L. VIT is going to cancel out because both these objects starts at 0 or starts at rest. So here I can just clean up. I can just say that the length of the ramp, or the distance traveled, is just 1/2 AT squared. Here I'm just going to go ahead and solve for AT squared by multiplying both sides by 2. The reason I'm doing this is because, well, 2 and L's are just constant. A is a constant for a specific shape, but both these shapes are different, so the A will be different in both these scenarios, okay? Because A is different, time will be different. Alright, other than that, I'm just going to go ahead and plug in A from my previous work in the other video. I know that for an object rolling without slipping, the function for it is just G sine theta over 1 plus C, as I've done the proof for that already. And T squared is on the outside of the parentheses here. Alright, so here I'm just going to really use it. I want to use it twice, right? So here, if you want to, you can. To what I did, I just multiplied the top both sides by 1 plus C, just so I can just get T squared by itself, and then divide both sides by G sine theta. So 1 plus C is a single term in parentheses. I just moved it to the top left, and then G sine theta, I move it to the bottom left. Okay, so this is where the statement comes from. It's really essentially, once again, I'm just doing algebra just to solve for the time square term. All right, now that I have that, I want to really use it for the sphere and the cylinder. So here on my work, I'm just going to use subscript S for sphere and then C for cylinder. 2L stays the same, same ramp, same angle, same G. So I'm just going to start canceling stuff that I don't need. The 2L's is factored out on both sides on the outside, so I know naturally they'll cancel out. Also on the bottom, as you can see, both terms have a G sine theta. That'll also cancel out. So essentially what's important here is just the 1 and the coefficient of moment of inertia, okay? Here in the work, I set it so that it's TS square to the ratio of T cylinder square, because in the question it says TS or T sphere first and then T cylinder to the right. So I'm just going to set it up where it mirrors what is being asked of me. But I highlight the square here because here my statement is for T square, not T, okay? But once you find T squared, to find T is super duper easy. So I'm just going to replace ts squared with the true statement. Like I said, ts squared here is just 1 plus c, the moment of inertia constant for the solid sphere, and that's down there. Likewise, the same trick is used here for t of the cylinder, which is 1 plus c of the cylinder. And here really is just plug and chug. Right? The coefficient for the cylinder is 2/5, and likewise the coefficient for the the coefficient for the solid sphere is 2/5. The coefficient for the cylinder is 1/2, and then this is 1 plus 2/5. So to find common denominator, 1 can be written as 5/5. 5 plus 2 is 7. Common denominator is 5, so it'd be 7/5. And then this is 3/2 on the right side, which you've done hopefully 3 times now. All right. And that 7 divided by 5 is 1.4. And then 3 divided by 2 is 1.5. At this point, you can crisscross multiply if you like, but I'll just reduce it this way. It'd be 1.4 to 1.5. Now, you might look at the answer choice and go, well, there's a decimal. Well, what you can do is just multiply both sides by 10, just so that, it mirrors. As long as you do legal algebra, things will be all right. So it'll be 1.4 times 10, which is 14. 1.5 also times 10 is just 15. So the ratio is going to be 14 to 15. However, you don't want to pick choice E because this is t squared, right? I want to point that out. The ratio that it wants us to find is just t. Well, the work I have here is t squared. Well, how do we get it so that it's just t? Well, just square root both sides. To get t by itself, you square root it, so it would just be the square root of 14 to the square root of 15. And that'd be answer C. Okay, so be careful with my strategy here. I saw for t squared, but the question asked for t, so just make sure you square root your final ratio at the very, very end. All right, other than that, that is the answer for this particular problem. Here, the next one I think is a little bit trickier. I'll show you a couple of different strategies to do this one. So here you have a rod, of mass 1 kilogram, of length 2, and this angle at some angle, and it's going to get released. The problem states at the very, very end where it reaches a horizontal position, the end of the rod is moving at a speed of 7 meters per second. So I want to point that out. That's super important. It says here, if the tangential speed of the end of the rod, right, not the entire rod, just the point at the very end of the rod, it has a speed of 7 meters per second. And it wants us to find what is the angle here that was released. So here, I'm just going to go ahead and draw stuff out for you. In order to find theta, you essentially have to figure out what triangle you have. I'm just going to go ahead and use half the length here because the whole length is 2. So from here to the center of mass, it's just going to be half the distance, which is just 1 meter. And here, I don't know what h is, but I can find h, So to find theta, you need at least 2 sides. Here, the hypotenuse is given from the pivot to the center of mass, which is 1, which is half the length. And then I need to figure out what h is. Once I have h, I can just do sine, because sine is opposite over hypotenuse. So really, in this one, I'm just missing h. Once I find h, I can unlock theta. So I'm just going to start with conservation of energy. Initially, the rod is angled, so it has to have some sort of PE referencing center of mass. But here, in this first strategy, I'm just going to show you how to do this based on the information provided in the problem. So initially, the rod is held stationary, so it has to have some sort of PE. Otherwise, there's no work done on it, right? The center of mass is a certain height above the horizontal axis or the ground. All right. So on the left side, it's just PE due to gravity. On the right side, it's just KE rod. So I do want to point out, because this is a rod that's pinned or is fixed to an axle. That means it's only rotating. It's not moving linearly. Like, it doesn't physically travel from A to B. It's just swinging. All right. So on the right side, there's only KE rod. Sometimes folks might goof and introduce KE linear, which is illegal. It's not moving from place to place. It's just rotating along a fixed axis. All right, I'm just going to break up PE into mgh. The mass is giving us 1, but if you follow along here, you won't even need it. KE rod is just 1/2 I omega square. So I just go ahead and break up I here is 1/3 because it's being pivoted at the end. The moment of inertia for our rod at the end is 1/3 ml squared, the length of the rod. And I highlighted here enough for omega, right? This is an important concept. As the rod rotates, its angular speed is the same for every single point because it traces out the same amount of angular displacement in the same amount of time. So omega is the same for every point mass on the rod because it traces out the same angle in the same amount of time. So therefore, omega is known as your angular displacement divided by time. So if angular displacement is the same and time is the same, omega has to be the same for every point mass on the rod. So therefore, I replace omega with v at the end over the length of the rod, because v is equal to r omega. So that if you solve for omega, it would just be v over r. So here, if you're going to use Vn, which is the information given in the problem, you also need to reference the n of the stick, right? You want to be consistent. If you're going to use the velocity at the end of the stick, you have to use the entire length of the stick relative to the pivot. So make sure you are consistent with these reference points. All right, other than that though, I'm just going to start canceling stuff out. M cancels out, and then L squared is also going to cancel out. Okay. Well, sorry, here I forgot that I did this for you. I just drew the 7 meters per second at the end of the rod, because that's what that's what's given in the problem. All right. Other than that, I'm just gonna clean it up. I'm just gonna cancel L square out, because here, the L on the bottom, the exponent on the outside, you're gonna end up squaring the top, and you're also gonna square the bottom. So L square and L square on the outside there is gonna cancel out, and then essentially V is gonna get square. So it would be 1 over 6 times 7 to the second power, because the initial speed of the end of the rod is given as 7. All right, I'm just gonna clean it up a little bit. To solve for H, I'm just gonna divide both sides by G. So here you have 7 square, which is 49. 6 is already on the bottom, and then you're gonna add the G to the bottom as well, or in this case divide both sides by G, which will make it 6G. And then if you just punch in 9.8 for G, it would be 49 divided by 6 times 9.8, which would be 0.833, and floating and running. So I'm just going to round out to just 3 decimal place there. All right, now that you have H, it's super light work. Once again, to find theta, sign would be appropriate here, because you know the hypotenuse, and you just found H being your opposite, so it'd be opposite over height. Well, your opposite here is just 0.833. Your hypotenuse is just 1, and then if you do, inverse sign there, you'll be 0.833 divided by 1, which is just 0.833, and then the angle will be about 56.4 degrees. So the answer closest to that would be C. All right. Here's another way to do it. I skip on the animation from the start there. So really, essentially, your starting point is the same. However, what you can do though is break up omega. Okay. I is still 1/3 ml squared. Omega though, what I did here is I'm going to reference the center of mass of the rod, right? So in the previous strategy, I used the velocity at the end of the stick, because that was given. If I use the velocity at the end of the stick, I have to use the whole entire length, because that's where the point is. But here I can reference center of mass if I wanted to, divided by r, right? Omega is simply v over r. The issue with a lot of folks is the consistency of how you interpret this information. So I'm just gonna do it. I'm gonna cancel out m here, and then I'm just gonna go ahead and make sure, well, I made a note for you here to make sure to reference center of mass if you choose to go this route, right? I think it's important not to just plug v in and not be consistent with what r is. So it's important that you make a choice and be consistent with it. So here in my work, on the left side, gh is carried down. 1 times 1 is 1, 2 times 3 is 6, and then the L squared term is right there. Once again, mass already cancel out. And then VCM here is going to get square. But here I highlighted R because, well, if I'm going to reference center of mass, the point for the center of mass is only a distance of L over 2 away from the pivot, right? It's just 1 meter. So make sure you are consistent with that. Here, I mean, for this one, you could just plug in 1, right? Because L is 2, 2 divided by 2 is 1. But I want to point out that if L is not 2, the strategy works. You would just take the length of the rod divided by 2 because that's where the center of mass velocity is referenced. All right, other than that, I'm just going to go ahead and flip-flop it. Here you have VCM divided by a fraction. So when you divide by a fraction, once again, multiply the reciprocal. So the 2 is going to go on top, the L is going to stay on the bottom. So this is what my work is. 1/6 is carry over, L squared is carry over. All of a sudden there's a 2 on top. That's because I multiplied both sides by the reciprocal. And then VCM stays on top. L here is on the bottom. But keep in mind, the exponent is going to get distributed to every term here, to the 2. The exponent is going to get distributed to the VCM and to the L square. Because I have an L square outside, I want to go ahead and cancel the L on the bottom, okay? So I need you to visualize that. All right, you can only do that if there's a square outside. So please make sure you do proper algebra. All right, so the only thing that's left over is, once again, the 2 is going to get square, which makes it a 4. and then the VCM square is going to make a VCM square here, and the 6 is on the bottom. However, the G on the left side will be divided by on both sides as well, just like in the previous slide. So it'll be 6G. So it'll be 4 VCM squared divided by 6G. VCM here, you actually know what it is, okay? So you actually know it's 3.5 or 3.5 because according here, I'm just going to put this back up. In the previous slide, I did this for you. The information given at the end of the rod is 7, right? But if you know the bridge function between linear speed and rotational speed, well, omega is the same as I stated in the previous slide. But when r goes down, then v has to go down. And this is a linear function. So VCM is half the distance, which means v is also going to be half the speed. So here, VCM at the center of mass is just 3.5 because it's half the distance away from the pivot. So it's going to move slower tangentially. Alright, so other than that, that's where the 3.5 comes from. And you just clean it up. If you do this on your calculator, you get the same height as previously, which is 0.833. And as you can see, same height, right? Same hypotenuse here still if you look at the small triangle. So sine of theta will yield you the same answer. Okay. All right. I hope that helps. If you need to watch these types of ratio problems again, I think it's super useful because there's really no calculations to be done except for just manipulating stuff. All right. Stay nerdy. Don't be whack.